Let's take a look at section 4.3, looking at logarithmic functions. So the first question here is, what if we have an exponential function? So something like f of x is 2 to the x. So we've been talking about those. So the question is, how can I find the inverse of that function? So remember how I do that. I reverse x and y. And then I solve for y. So the question is, how can I solve that equation for y? I mean, sometimes people say, well, I could take the y root. I mean, I could do that, but I'm not solving for y then. I'm actually solving for 2. So actually, we need something new in order to solve for y. So what we do is we define a new type of function, which is the logarithm. So we say if x equals b to the y, then y is the logarithm base b of x. So we read that. Y is the logarithm base b of x. Okay, so that's our little definition. Okay, so how do we finish solving this particular example? Then this one would be y is the logarithm base 2 of x. And so we found our inverse function. All right, so one thing to notice here, so if I have an exponential function, its inverse is the corresponding log function with the same base. So actually, I mean, if I have the function like 5 to the x, I could tell you immediately its inverse function would be a log base 5. If I had the function 12 to the x, I can tell you immediately its inverse would be log base 12. Okay, so exponentials and logarithms are inverses of one another. All right, now let me see if I can come up with the graph of this log base 2 of x. So how can I come up with that graph? Well, based on what we have so far, well, I know that log base 2 is the inverse of the exponential 2 to the x. Now, I know what that one looks like, right? So what if I go ahead and I graph this function? Okay, I'd have 0, 1, 1, 2, and negative 1/2. So that's my exponential function, my 2 to the x. Looks like so, right? Remember, the exponential functions have a horizontal asymptote at y equals 0. So then how could I get the graph of the logarithm? Well, I would just reverse the x's and y's, right? Let's see, that I'd have 2, 1, 1, 0, 10⁻, -1. So there's my graph of log base 2 of x. So you'll notice there, because I reversed x and y, the horizontal asymptote at y equals 0 is now a vertical asymptote at x equals 0. Okay, so you kind of notice a pattern. So if you look at this graph of this logarithmic function, kind of notice a pattern with these points. So actually look, say you wanted to graph something like log base 3 of x. Well, look at this point over here. See, this is the base, comma 1. So wouldn't the point on this graph be 3, comma 1? Look. The exponentials always have a y-intercept at 0, 1. So the logarithms would always have an x-intercept at 1, 0, right? This guy is 1 over the base, -1. So wouldn't that be a third -1? So there's the graph of log base 3. And so that has that vertical asymptote. X equals 0. Okay, what about log base 5? That's going to be really similar, right? Then I'd have 1, 2, 3, 4, 5, 1. I'd still have 1, 0, and then I'd have a fifth -1. Something like that. Three and 4 are our two special logarithms. So there are two logarithms that come up often enough that they're given a special designation. So one of them is number 3, and we call number 3 the common log. Okay, so this looks like it's a log without a base, but actually that's impossible. So when you see this, we're assuming that you know the base is 10. So log base 10 is just written as log, okay? So if I try to graph that one, log base 10, so my points would be at 10, 1, 1, 0, and then a 10th -1, so way over there somewhere. Something like that. That's the common log. Okay, my other special log is the ln. This guy's called the natural log. So ln stands for like logarithmic naturalis or something like that, but it's the natural log. So this guy comes up often enough that it's given its own designation, and this guy is a logarithm with base e. We talked about e in the last section. So whenever we have a logarithm base e, we write that as an ln, okay? So if I'm graphing that one, well, my first point would be at e1, so that'd be 2.71. So let me see, different color. 2.71-ish, so that'll be here. On 0, and then close to a third, -1. Okay, so there we have the shapes of those logarithms. And those are pretty easy to come up with, like I said, if you just remember that pattern. So let's look at just a couple of transformations problems. So graphing number 1 here, I'd start with the base graph. Okay, so I just have to remember my pattern. Okay. And then let's see, I have a shift left 1. So I'd have -0.5, -1. 0, 0, and 1, 1. And then last step, move down 3. So the vertical asymptote is going to stay here at -1. Move my points. Something like that. So I've got enough to graph that I think. I'm just curious about one other thing. I'm curious what the x-intercept is going to be. So what if I set that whole function to 0? Two cubed. It's going to be 7. There's that logarithm shape. Okay, what's the domain of that one? -1 to infinity. the range for all logs would be negative infinity to infinity because these are the inverse of exponentials, and exponentials have a domain, all real numbers, right? So remember, we're swapping domain and range with inverse functions, right? Okay, should I try another one? Let's try number 2. So this guy, the base graph would be ln of x. Remember, that's the same as a log base e of x. So what does that look like? Got e1. It's about 2.71. 1, 0. 1 over e negative 1. That's like pretty close to a third negative 1. Okay, then let's see, we do our multiplications. So here we actually have 2 multiplications. So let me move this unit down. So maybe I'll do the negative next. So that negative is outside. It's multiplying all the y's by a negative. So what I'm actually doing here, I'm making all the y's negative. I'm reflecting over the x-axis. And then 1 over e, 1. Okay, then multiply by 2. Remember, I have to do all my multiplications before my additions and subtractions. Okay. Multiply all the y's by 2. This is a vertical stretch. So I'd have e negative 2. So it's 2.7 negative 2. One, 0. And 1 over e2. All right, and then right 3. So I'll do that step over here. There my vertical asymptote moves to x equals 3, right? Then I'd have 3 1/3, 2, so that's 7/3, 2. And then 1 0 is going to go to 4 0. And then e negative 2 is going to be 5.7 negative 2. In exact form, e plus 3. All right, and then our very last step, shifting up 1. Okay, so I've got 7/3, 3. And then 4 1. And then 5.7 negative 1. And then I finally have a nice final graph. The domain would be 3 to infinity. Over the range, we said negative infinity to infinity for all logarithms. Okay. So this is our final graph for that function. All right, so what if we just want to find the domain and we don't necessarily want to make a graph? So the first couple here are really simple. I already know what log base 2 of x looks like. Looks like this, right? Doesn't ln of x look pretty much the same? So actually for those, since I know the vertical asymptote, don't I know the domain immediately? The domain is just 0 to infinity. Even something like number 3, you can tell what that one looks like really easily too. It looks like a log but shifted left 4, right? Look like that. what about something like number 4? Now, I don't really want to graph that. I mean, I could, but I have a whole series of transformations that I'd have to go through there. So what's another thought? Well, the thing is that the domain is interested in the x values. So the only transformations that affect the x are the ones that are inside the argument to the logarithm here, right? And then if you think back to these first couple, look, whatever it is that's inside the log has to be greater than 0, right? Think about those graphs. So actually, in general, to find the domain of logs, I can use a simple rule. I just take the inside, set it greater than 0, and solve, and then I'm done. So that actually makes it really easy to find the domain of logarithms. So I mean, if you think about it, that's really what I did in these last couple. Like, if I go back to this one, look, really isn't what I did. I took the inside, set it greater than 0. It was just so simple I didn't have to write it out. Okay, so for this guy, take the inside of the log, set it greater than 0. Don't forget, when you divide by the negative, you have to flip the inequality. And so there's my domain. So the next thing is, even with the more complicated problems, as long as I'm looking for the domain of a logarithm, I use the same rule. So when I'm looking at, say, number 5 here, I'm still looking for the domain of a log. So I still take what's inside the log and set it greater than 0. But this is a little different because now I have one of those rational inequalities. So remember when we talked about these? Remember how you solve these? You have to use a sign chart. Okay, so I test something. 0 would be a nice one to test. If I plug 0 in there, I get a negative. Both multiplicities of top and bottom are 1, so the signs alternate. Okay, and then remember, I'm looking for where this thing is greater than 0. So the domain would be negative infinity to negative 4, and then 2 to infinity. There's one more here. Let me move this down. This is actually an easy one. So I'm looking for the domain. But what kind of function is this? So be careful. This is not a log function. This is an exponential function. Do you remember the domain of exponential functions? All real numbers. That problem is easy. Okay, let's look at a couple where we're just changing between exponential and logarithmic form. So this goes back to the definition of a logarithm. Remember how we started this out? We said if x equals b to the y, then y is the log base b of x. Okay, so I have the exponential and the logarithmic forms that I can interchange between the two. Here's the way I remember this second rule. See how the y here corresponds with the exponent up here? So I remember this, the exponent is the log. Now the base of the log is the same as the base of the exponential. So that's just the base there. And then the x in here is whatever was on the other side. So this is how I remember, this is the way I remember how to change into log form. This little rule here. So if I'm looking at these first few up here, these guys are in exponential form. So to write this in log form, I'm going to use that rule. So the exponent is the log. The base is 2 of 8. This guy would say the exponent, y, is the log base e of 3. But then remember, log base e, we write that as ln, natural log of 3. This one would say y is log, that's a 4, isn't it? This guy would say 4 is log base 10 of p, but remember, log base 10 is the common log, so we just write that as the log of p. And then these last three here, these guys are in log form. So it's actually even easier to change into exponential form. So here's the way I remember that. This guy down here is the base. This guy's the exponent. So wouldn't that just be 3 to the negative 2 is 1 over 9? Okay, ln is a log base e. Be e to the 4th equals x. Common log is a log base 10. 10 to the n equals p. It's pretty easy, huh? Okay, let's do one more thing. What about some evaluating? So when we say evaluate, that means my goal is to actually find the value. It should be a number. So if you think about what a logarithm is saying, think about if I set that equal to something and I change it into exponential form. Isn't that saying 3 to what number is 9? Well, 9 is 3 squared, so isn't y just equal to 2? Right, 3 squared is 9. So like this next question here, this is saying, the question is 10 to what power makes 1 over 100? Okay, I know the answer. The answer is negative 2. I mean, I can start by writing something out. The base is 10. 10 to the y equals 1 over 100. So let me see. And then to get that 10 up, then my exponents would have to be equal. Y would have to be -2. Okay. Change into exponential form. So I'm going to make both sides base 2, so I have a common base. Because then I can conclude that the exponents here would have to be equal. And so y would have to be 4. So let's see, is that true? So what we're saying there is, what is root 2 to the 4th? Well, that's root 2 squared squared, right? Oh, it is 4, so checks. Okay, ln is a log base e. This is saying e to what power is the 4th root of e? Well, isn't the 4th root the exponent 1/4? So wouldn't the y be a 4th? I have a common base. So this is saying e to the 1/4 is the 4th root of e. That's true.